Hi, this is Professor Cummings, and this is another video for Strength Materials. It's going to be one of the first videos that you're going to see in the series, our earlier part of the series. It's more relevant in the earlier part of the series because we're going over key terms and basically how to set up a problem. Now, not all problems are going to be set up like this, depending on the layout of the component we're looking at. That this is a pretty good template for how a problem is going to be set up, as well as all the terms that are going to be getting used here are going to play a major part in the rest of the class. So let's go here and we'll get you to the objective. So here's what we're going to cover in this one. We're going to go over the equilibrium diagrams in a deformable body, look at the types of loading conditions, the types of reaction forces, break those down a little bit, look at the method of sections, which is going to be a major part of the class, and then sign convention and some concept of deformation. So really these are going to be terms that we're going to use throughout the rest of the semester. They might change a little bit in terms of how you apply them, but the general terms are going to stay the same. But first we're going to look at the whole concept of equilibrium. Now, in this class, we're going to look at most of our problems in the state of static equilibrium. Now, if you have a rigid body or even a deformable body, and you're looking at it in terms of this strength material class, when I say static equilibrium, what I mean is that the object is not being put into motion. It's not being accelerated. It is basically staying kinetically put. It's not, so all the forces that are being applied should summarize to zero, and any of the moments that are being applied to the object are being set to zero. And I like this example here in the lower right of a bridge. Bridges aren't supposed to slide and move and rotate. They, for all intents and purposes, stay put, even though you can see a bridge sway and deform. So it means that, kinetically it is in static equilibrium. And when we describe this as static equilibrium, we can think of it in the Cartesian coordinate system, the X, Y, and Z coordinate system. We can think of this in terms of motion. So if you have an object and it is literally moving, sliding, falling, or whatever, you can break it down, all of its motions, into 6 degrees of freedom. And those 6 degrees of freedom gives you 6 kinematic or 6 equations for static equilibrium. So we can break it down into the 3 translational directions, X, Y, and Z. That's just your normal coordinate system. And then the other degrees of freedom is rotational. That is going, rotating about the X-axis, rotating about the Y-axis, and rotating about the Z-axis. If you think of those degrees of freedom, that is all the degrees of freedom that anything has when it moves. It can, go in those 6 degrees of freedom, and that creates these different kinematic equations, or equilibrium equations. So the sum of the forces moving in the X direction should be 0. Sum of the forces in the Y and the Z should be 0. So those are all your translational equations. And then the rotational equations are the bending moments, or the rotational should come down to X, Y, and Z as well, on about those particular axes. And again, the resultant is just the net force that acts from all those different coordinates. So if you have a object and it's got a load on it coming from another direction that's not perfectly aligned with an axis, it will have a resultant force that you can use these 3 axes, or I can break it up into different vectors, and that's your resultant force. Now, that's, the summation equations for equilibrium. Now let's look at the different types of loading conditions. And there's a few different types. There's actually 4, but I'm going to break it down and give you 1 initially and then 3 more that follow that I want to break up. And I'm separating this out because it kind of fits its own little category. The first type of loading is a result of it is a bending moment. We talked about that in the last section. So a moment, and all a bending moment is a reaction induced in the structural element when an external force, or a moment, is applied to an element causing the element to bend. So You can think of it in terms of this hoist and holding up an engine. Now, there is a external force, this engine, and it is going down, pulling down a downward force due to gravity. And what it results in is a bending reaction. Now, it might not be perceptible to the naked eye, but it is a bending moment taking place in this setup. Now, that's an exaggerated view of what that bending moment would look like. And you can calculate that bending moment. It is whatever the load this is, the weight of that engine, multiplied by this distance about this particular point, or a particular point, this origin. So the force times the radius, and that radius is from that reference point. Typically in most of your kinematic and static and dynamic books, that is just called a reference point of O. Again, in a static equilibrium, the sum of the moments should equal 0. So where there's a moment here, there is a reaction moment taking place within the material that counterbalances it. And the sum of those, one positive, one negative, or several positive, several negative, depending however this moment is going to be summarized, should come out to 0, or will come out to 0 if you're in static equilibrium. Now, then that's one. Now, here are the other 3 types I want you to be aware of. One is the external loading, also known as surface loads. Then you're going to have another type of load you'd be concerned with, which is your support reaction. So if you have a physical body, you've got surface loading on that body, on that structure, that bridge, that axle, that table, whatever, it's going to have an external load applied, or a surface load. It's also going to have a support reaction, from that. And you can see this again in a lot of your kinematics and statics classes. And then there's a third one that is a little less intuitive, which is the internal reaction. Now, I have this diagram here that shows the different types of certain type of loading. These are called distributed loads. There's 2 primary ones that we're going to be concerned with. One is a rectangular load, which is also called a uniform load. It is made up of a load that goes it's distributed across a surface of a certain length, and it is rated by load per unit length. The gradient load, the triangular load, has the same concept of a load per unit length, and it is going from 0 up to a maximum amount. And it's also got a measurement of load per unit length. Now, down here below, you have a combination. It's called a trapezoidal load, and you treat it as 2 different loads. You treat it as a distributed or uniform load and a gradient or triangular load. Now, the thing about both of these is with a uniform load, because it's uniform, because it looks like a rectangle, you can treat it a lot like a rectangular, or, the geometry of a rectangle. So that means your load is going to be uniform in the middle, and the way you find what is at this point this R value, or an effective load, is the multiplication of that distributed load, the load per unit length, by the actual length, and you end up with an effective load that is in the center of this distributed load. Same goes with the triangular load, or the gradient loading. It's a load per unit length. And since it is based around a triangle, you can find the effective or resultant load with the area of a triangle. 1/2 the base, which is the length, times the height, which is the maximum load. And that'll get you that resultant. And where it lands is 1/3 away from the heavy end, or 2/3 away from the light end, which would be the centroid of that triangle. And when you're dealing with the trapezoidal load, you need a combination of those 2. So you can't just treat it as a singular load. And there is an equation that does actually take those into account to give you one single effective load. That we'll pass through that, but we won't use that in class. So going more into this, again, we're still talking about static equilibrium, but when you're dealing with a potentially a deformable body, you can get things such as, which we'll go through in the next chapter, things such as a part bending, flexing, or changing its shape, but it's still going to be in static equilibrium. So here's some of our definitions. Put those in red. The surface load or external loading. These are forces that are acting on the body. They can be distributed or concentrated. And then we've got body forces, which is things such as the weight due to gravity, which would also, fall under, even though it's part of that, it's still considered an external load. So if those, fall under that first category. And then we've got something called the support reactions. Now, when you look at this through statics, your statics class, which is, one of your prerequisites, that would be where you'd have a weight or body forces, which also falls under your external, and you're going to have a normal force coming back, reacting. So and same you have with this little free body diagram where you have the weight, the body forces, and a normal reaction force. So you got this concept of the equal and opposite that you learned in your statics classes. So going a little bit more into some detail, just to kind of cover things a little bit more. This is your concentrated load. So another, your example of surface load, external loads, and they're not considering the weight in this particular case necessarily. So this would be a concentrated load, that we looked at in the beginning. And then this is, supported at a specific point. And you got the distributed load. And notice the units: force per unit length, force per unit length. And down here, you got force per unit. So 5 newtons per millimeter, and it is 6 millimeters distributed across 6 meters. And this would be the effective load. So, 30 newtons. So again, that's 6 times the newtons, 5 newtons per meter comes out as 30 newtons. And this is just how that problem works out. How you went from this to this effective load acting in the center of the 6 meter distribution. So 5 newtons per meter, 6 meters across. So 5 times 6 is 30. And notice the units cancel out. So that's how you end up with an equivalent or effective load of 30 newtons. And just another picture of distributed versus concentrated loading. You see in this picture here, you're distributed across the truck bed, whereas you're concentrated in the middle. So again, these are your distributed versus concentrated loading. And here's the picture I promised you, distributed versus concentrated loading. So you could have a concentrated load, also called a point load, uniformly distributed load. Again, this is your effective loads on this side on your right, and this is the type of load over on the right or on the left. So you can see you've got a distributed, uniformly distributed load, triangular or gradient load, and this one is 1/3 from the heavy side, 2/3 from the light side. And this is the more complex equation of a combination or trapezoidal load. What they did was this is the resultant of using a distributed load with a gradient load on top of it. And if you follow this equation, you can find out where that net effective load would end up. Now, we were talking about the surface loads, our external loads, and then we went into our reaction loads. So I want to go into a little more detail in that. It gets a little more complicated than just the simple picture of force versus normal force or weight versus normal force. So there's a little bit more that you're going to see when you try to work an actual strength of materials problem. So again, remember you've got an external load or a surface load. They could be concentrated loads or a distributed load. But you're also going to have a reaction that's taking place. And you're going to have to consider what's happening with these support reactions. Now, again, remember you're still in static equilibrium. So whatever load you're affected or you're getting here in the surface loads, you're going to have an equal and opposite reaction load in order for this thing to not move. It's just like any static problem you've worked with in your statics class. So in support reactions, no movement takes place. It's in static equilibrium. So you're going to have a load and a reaction. In this particular case, both of these is just 2 points of reaction. That's where you're being supported. So that's where your reaction load is taking place. And again, the sum of those forces are going to be 0. Now, there's different types of surface and different type of reaction supports you're going to run into, which is going to give you a result of different types of reactions, support reactions. So that the type of support you're dealing with is going to be a very significant thing in how it's going to give you a reaction load. So if the support prevents its translation in a given direction, then a force must be developed on that member in that direction. So think of it this way. When you're standing on the surface on a floor, there is a reaction coming back at you upward, right? So as your force is coming down, there's a reaction coming up from the ground. We call that the normal force. If you were to lean against a wall, you're applying a force against that wall. The wall's preventing you, and so there's a force, a reaction force coming back in the other direction. And the same goes if you're dealing with a rotational force, if there's going to be a moment coming back the other way. Now let's look at some of these. So you got on the left side, you've got the type of connection, type of support. And on the right side, you've got the type of reaction. Same goes around this portion here, connection, reaction. And look at what you're dealing with as far as the support versus what type of force reaction you can expect from it. So here you've got a cable at an angle theta holding up a beam, and the support reaction is what's resisting at theta. Here you have a roller, which is a single point, or you've got this smooth support at an angle of theta, and the reaction from this roller is a normal force coming back up in the other direction. Same goes with the support. You've got a reaction coming back off of this surface, which would be normal to this surface, angle theta. Now, you notice that you're only seeing one reaction coming back. You don't see, especially in this roller, you're not seeing a reaction coming in the X direction, just in the Y. That's because nothing in this roller is resisting in that direction. You can only get that reaction where there is resistance. Same goes with the journal bearing. Journal bearings are designed to support you in one direction, and that's what you're seeing here. You're seeing one direction. Now, over here on the right side of this table, you've got different types of supports. You've got pins, and if you look at this pin, what's it doing? It's resisting you coming upward and down, and left and right, X and Y. So where are your reactions? You're getting a reaction in the X and an action in the Y. There's no moment resistant here. Same goes with this internal pin, X and Y only. At the pin, you can still rotate. Now here you have a fixed support, which is a cantilever, and you have a reaction in the Y. The wall is preventing you in the Y direction. It's also preventing you in the X. And because it's embedded into the wall, it's preventing you from a moment, so you can't rotate. And then you've got a thrust bearing, which, the nature, the difference between that and the journal is it stops you from thrusting or thrust forces in the X. So X and Y. So again, the support demonstrates what it's resisting you. So that's what the reaction force is. Now, there's something before I get into the third type of loading, the third type of force loading, I want to start with method of section. These two things tie together as far as how to solve a problem. So what the method of section is a tool you're going to use quite a bit in this class of looking at the internal resultant loads. So what you're going to do is use this method of section to find the internal resultant forces and moments that go on within a body. So this is, again, all three. And the way to find that is through this method of section. So remember, if we look at this truss, just everything in black is the truss. Looks like some sort of a bridge. You've got certain external loads, support loads, or surface loads of 10K or 10 kilonewtons that are acting at point B, point F, and point E. Those are external loads. Well, because of the way this bridge is sitting, maybe it has a drawbridge effect. It's being supported at one end here with 15K reaction and another 15K reaction here, but maybe it rotates. Maybe this is a hinge, so you've got some sort of a reaction here at A. So these are all reactions. You know, if this were a hinged bridge, as it sits down, you're going to have, again, remember, sum of forces, you know, 10 coming down, 10 coming down, 10 coming down. So that's a sum of 30 and an equal and opposite of 15 and 15. So 30 going back. So it's in static equilibrium. And because of the way there's external forces are all going in the Y direction, the one reaction that hinge would have in the X direction is 0. But there's something else. Let's say you wanted to find out what was going on in these members inside of this truss and the bridge. Well, now you've got something called the method of sections, which is essentially like slicing the members apart and looking at what what's going on internally, what type of reaction forces are there. Now, why would you want to know that? Because this is how you decide whether or not a member needs to be redesigned, whether or not it needs to be beefed up, you know, whether it's capable of taking the load that it's going to deal with internally. So those are your support reactions in gray. And then you get the internal resultant loads through this method of sections. Now, with all this, you're still solving problems. And since you've got things potentially going in two different directions, you know, you can have loads going down in the Y or to the right in the X, or you can have a rotation counterclockwise or clockwise. You know, you're going to have reactions coming back the other direction from external loads, you know, positive up in the Y and maybe to the left in the X. So you're going to have different, you know, all this opposition going. So you need to know what sign to attribute to things. So the coordinate system you're going to use, since we're dealing with a two-dimensional Cartesian coordinate system, is going to be important. You're going to have to establish this in your problems. So the sign convention is going to be important. Again, everything is going to be equal out to 0. We're talking about static equilibrium. So this is our typical sign convention. Typically. Now this can change. If we have a problem with an angle in it, usually you will rotate your coordinate system to match. But by and large, you usually have a positive going in the up direction, positive going in the Y direction for the X, and you go counterclockwise in the Y. Now, like I said, there are changes. The real key here is to be consistent with your coordinate systems. If you're going to change it, maybe there's some reason you want the positive to be facing down and X-axis going to the left, but you've got to maintain that throughout the problem. Otherwise, you'll start to run into sign errors and potentially have major problems with your solution. But looking at just the moment section of this, which is a little bit, sometimes can be a little more confusing. If we look at going clockwise or counterclockwise as positive, and that is the way most problems are set up, you can think of it as with these two smiley faces. And when you're going in this direction, you're positive, and when you're sad or upset, you're going clockwise or negative. So when you're looking at bending moments, counterclockwise is positive and clockwise is negative. So if we were to look at this beam, you know, we've got the load, the effective load, and the support reactions. You're also going to have a bending moment, potential bending. So as this comes down, this theoretically will start to sag, and you're going to develop a bending moment. This is actually creating a moment about both of these 2 points. So again, that's your effective load, P times L. You're going to have a reaction at A and a reaction at B. Nothing is going on in the X, so your sum of forces is 0, and since you don't have enough an external load in the X direction, that one falls out. You have your sum of your forces in the Y direction should be 0, so that means that the reactions, both going in the positive direction, and this one going in the negative direction, should equal 0. So reaction at A plus reaction at B minus the load should equal 0. They should balance. So that load should be equal to the reactions at A and B. Now, if we wanted to find out how to solve for that, what we have to do is assume a moment about either one of these points. In this case, we're going to consider it about point A. Now, if we use the equation of distance times your load, then the load at A goes to 0 because the distance is 0. The load at B is the reaction at B times at L. So that means that we've got a bending moment going counterclockwise. And the load at C, the load from the applied, our moment is this load, since it's going down, times this half of L. Let's took that in the negative direction. So it's going down in this direction, rotating clockwise. And from that, we can solve for the unknowns. And that the load will summarize at 0 again. So our method of analysis, so this is the last part of this presentation, how we actually set up the problem. So the first thing you want to do is you're going to need to find your support reactions. So you have to set up your free body diagram. When you put all your external loads on your free body diagram, you can start to look at, see what your reaction forces would be. Now, if you have a section of interest that you're concerned with, now that you've got, your reactions and your external loads accounted for, in the free body diagram, you can, get your resultant loadings. You also have to set up your coordinate systems, and your moments should be summed up at the section of your concern where the resultants act to eliminate any of the unknowns. And the negative values for the resultant, the actual direction is the opposite from the free body diagram. So this is Professor Cummings, and again, this is to give you some key terms we're going to be using throughout the semester, as well as some of the things to look for when you set the problem up that you're going to be concerned with. Again, thanks for watching, and I'll talk to you soon.